what is going on? So for this problem, I'm going to do it like this. So let me give this a thumbs up. So this problem has a little, I call it array partition 1. Given an array of 2 integers, your task is to group these integers into n pairs of integers, say, which makes the sum of min for all I from 1 to n as large as possible. So 1, 4, 3, 2. So the best way to do it is to pair it like this: min 1, 2 plus min 3, 4. N is possible. The range of it is 1 to 10,000. The integer range of the arrays is negative 10,000 to 10,000. Go over my first approach. My first approach was, well, because I was trying to learn counting sort, I was going to use counting sort. But I realized pretty quickly that using counting sort was going to have a horrendous time complexity, because the time complexity for counting sort, and I don't know if I can describe this that well actually. I'm going to make a video on counting sort, because I'm working on learning counting sort, and right now, so I'm working on a video for that. But it's going to solve another problem, because it doesn't work in this problem, and the reason why is because counting sort requires a time complexity of O(n) plus k, where k is equal to the range for the values of the numbers you're sorting. But the range of values can go from 10,000 to negative 10,000, sorry, to 10,000, which is a range of 20,000. And suppose your array is size 3, right? That's pretty ridiculous. Like, basically, it's not even running a linear scan with respect to, oh sorry, it can't be size 3, it has to be an even integer. But that's a ridiculous disparity, because then your time complexity is O of 4 plus 20,000, which is just astonishing, because it's not at all linear with the size of the array. And if you can look here, notice it's not efficient, because the range can be very, very large, like say in the n. So let's say k is way larger than n. I mean, you can suppose k is about n to the 10th power, right? If you suppose that, then if there's a linear scan, it'd be O of n. But if you do this, I think you end up getting O of n to the 10, which seems not even quadratic. That's worse than quadratic. I guess it is polynomial, but yeah, it's not the best time complexity for this problem, because you have such a large range. I think these are more useful when you have a small range, like maybe the numbers are only single digits, 0 to 9, which I'm not 100% sure, because I'm about to learn it, but I think radix sorts take advantage of that, because I think you deal with only digits 0 to 9, so that's why counting sort is efficient there. But because then k is like almost a constant. But if k can be really large, it is not going to be so efficient. So for this problem, it's not super efficient, so I didn't do it for this problem. Instead, there was another way to do it, which is this. Oh, I already have my answer here. So I'll show you how I kind of came up with it. So I had already realized the pattern here. So if you look at their example of 1, 4, 3, 2, there's a pattern here where basically if you order these, all you need to do is take the sum of the even index values. So take 1 plus 3 equals 4. And you can do this for anything. So like even if you have just 1, 1, 1s, it's 1 plus 1, right, is equal to 2. So you're always taking the even index. So like you take the value at index 0. So like what I would do here is I'll sort. So I'd say step 1, sort, and then step 2, I would sum up over the even indices, like 0 to, it only goes 0 2 here, 0 2. Okay, let's show how I would do this. So the first thing I would say, okay, well, I need to sort nums. So we'll do sort nums. Then I'll say for I in range 0 to length of nums and increment by 2. Basically take the sum s equal to 0, and this will give me s plus or equal to nums I. And then return s. So this should work, and if we look at the time complexity, analyze the time complexity for this, to sort is O of n log n, so we sort it in O of n log n, then we do this, which is, what is this for? This is for something else. This is for if I'm slicing, but I'm not slicing here, so here's O of n log n, so I'll write down, so this is O of n log n, and then by iterating through it, it's going to be O of n divided by 2, which is the same thing as n, oops, O of n. So we do that, so I think n log n is a little bit larger than n. So it looks like the time complexity is O n log n, and yeah, so we have that as our time complexity, but also we don't have to do it this way. So this, you see I'm iterating through like this. We could also take num sort, we could create a slice of nums too, right? And all we need to do is increment it by 2. Yeah, so if you print this out, it will only, we're not going to need this, it will only, it'll increment it by 2, that's our step size. So let's start at index 0, and I go to index 2. Oh, what's my test case? Huh. Interesting test case. I should have put this one. Yeah, so it goes 1 and then it goes 3. And I could just sum that. And then, I mean, if you've already gone this far, you might as well just do this. You might as well just return sum. Sorted is going to return a nums and then slice it. And then sum up those sliced ones. You might as well just do that. And this actually works. So I submit and that will give me the answer. Yeah, this is a cool problem. I like this problem. But yeah, so that is how you would, these are some things to think about if you're going to solve a problem like this. So some things for consideration. So yeah.